Now, one of the trig integrals that I didn't talk about yesterday was using substitutions involving t results, which of course is quite a valid way of doing things. Keep in mind this, if t is tan x on 2, that's why our standard substitution for t results, then sine x, remember, is 2t on 1 plus t squared, cos x is 1 minus t squared on 1 plus t squared. Haven't bothered with tan x because we use this for integrals that involve sine and cos. And remember, dtx, we can eventually come down and show that dx is 2 to t on 1 plus t squared. Okay. So let's do an integral. So something like this. Cosine's there. I can't do a u equals cos x because there is no sine there. There's no, it's not cos squared, so I can't use a trig identity. There's no other trig function. I can't play with it. So I'm going to use t results. T is tan x on 2, which means dx is 2 to t on 1 plus t squared. So I substitute in, the dx becomes 2 to t on 1 plus t squared. My cos x becomes 1 minus t squared on 1 plus t squared. I end up with a polynomial to integrate. Multiply top and bottom by 1 plus t squared, and I eventually get 2 over 13 plus t squared, which is just inverse tan. So I end up with 2 on root 13, because remember 1 on a when we're dealing with inverse tan. Inverse tan of t on root 13. Well, t is the tan of x on 2. So it's an interesting expression that we end up with, but there it is. 2 on root 13, the inverse tan of tan x on 2 on root 13, plus a constant. So this is for dealing with trig integrals where we can't use identities, we can't use substitution, well, our normal substitution. Bring it back to the t results and we'll turn it into a polynomial and see if we go there. But of course, remember, I did t equals tan x on 2. It doesn't have to be tan x on 2. If your angle was 2x instead of x, you might want to use t equals tan x, in which case dx becomes dt on 1 plus t squared. To generalize it, if you were going to use t equals tan x on a, you will end up with dx being a dt on 1 plus t squared. Okay? So we normally see tan x on 2 and we end up with 2 dt on 1 plus t squared. But there's no reason why it has to represent x on 2, because we're just talking about double angles and half angles. So depending on what the question originally has, we just halve that. So if it was sine, I don't know, 10x, we could let t equal tan 5x. And then if it was tan 5x, then a would be 1/5, of course. And I'd end up with dt on 5 for 1 plus t squared. Yep. Right, so the a matches whatever x is divided by in our substitution. That's what will be on top of the derivative. Okay, that's it. That one was just a quick little one to